Okay. Hi guys. I think you can see my screen now. Yeah, and first of all, I want to start with congratulating all of you guys for being selected for this limit camp. I hope you all will enjoy the lectures and the content we are providing here. And we really believe that they will be helpful for your mathematical journey someday or the other. Okay. And also, I hope you all guys are doing well in the period of lockdown. It is a weird time. Yeah, so lots of things are happening now, but I think you all are doing well. Okay, so today we are going to discuss about metric spaces. And this is a topic which we actually do in our mathematical analysis studied in the bachelor's course of any maths degree. Yeah, and we are going to discuss like a brief introduction to this we are going to have here, like how we think about this and why this is important to study, mathematically important to study, and all such things. We are going to discuss it here. Yeah. So, and the thing is, you can see me right now, but I will stop the video because it might be a disturbance when I'm going to discuss the content. Then there is no that importance that I am showing myself. Okay. So let me just stop my video and then we can start discussing our content. Fine. Cool. So we are going to discuss metric spaces and we can have an analytic introduction of it. And to just introduce myself, I am Soham Bakshi. I am a student of BMath of Indian Statistical Institute. Okay. So let's start with the lecture. Firstly, we are going to have this thing, what we already know about R. We are going to discuss few things on this. So you guys are in mostly class 11 or standard 11 or standard 12. So you guys should have a basic introduction to the real analysis. That is the calculus we do in 10+2. So there we learn several things like differentiability, integrability and all. So firstly, we're going to discuss, like have a quick review of all that. The analytical things we know about R. Okay, so firstly, we're going to see what we know about R. Then we are going to see a motivated generalization. Okay. And then we have examples of metric spaces. Then we have things we can do in a general setup, like when we have a motivated generalization, then what we can do sitting on that generalization. We are going to discuss a few of them. And then we will end by having a glimpse to topology. That is also a very analytical subject, what you are going to learn in the bachelor's course or maybe master's. So it is a sophisticated maths and we are going to learn the glimpse to it. We're going to have a glimpse to it. Okay, fine. So let us start with the knowledge of R, our knowledge of R. So this presentation won't give all the details of the lecture. So I will jump sometimes from this presentation to my blackboard. And in the blackboard, we will discuss something and then again come back to this presentation. This is our reference presentation. We can think it is of a reference presentation. Fine. So to start with our knowledge of R, we know something as the limit of sequences and functions. That is something we know. At least we expect you to know, but yeah, we'll give a review of it. Then there is something called limit point of a set. This is not very much discussed in the 10+2 level, but yeah, we will say this. Then we have continuity, differentiability, integration. So all of this we have in our set of real numbers. Like set of real numbers or functions defined from R to R. We know what do we mean by continuity of such functions. We know what do we mean by differentiability of such functions and integral also. So you have learned all these things in 10+2, almost. Okay. And as you guys are like, you all have qualified with for the limit camp. So, and we also in our syllabus of 10+ category 2, we had this all of these things. So I think you guys should be a little bit at least comfortable with this. So I won't discuss them in full details, but I will go through a quick review of it. Okay, so let me share my blackboard. So, and I will go through each and every such topic in a quick detail. Okay. I hope you all can see my blackboard right now. Okay. So we are going to start with defining. So properties of R. Not properties, maybe. Analysis on R. Okay. So here, first let me define a sequence. So I think you already know it, but let me again define. So basically, we are going to see all those things which we can do on the setup of R. We know what we mean by a set of real numbers, and we are going to see what all we can do here. What all analytical things we can do here. So firstly, we can define a sequence on it. That is, we can just define sequence on any set rather. So that is a xn, where xn is our real numbers. So these are sequence like x1, x2. So you can start with it n greater than or equal to 0 also, then the sequence will start with x0. That doesn't matter actually. So this is a sequence on R. So then we know what we mean by a sequence to be convergent in R. So that is, we say like, we write like this. The xn sequence is converging to some x, where x is in R, as n tends to infinity. This means that xn is converging to x. So the definition of it is, for all epsilon greater than 0, there exists n epsilon natural numbers. So this n will depend on epsilon. So this is n epsilon, such that xn minus x is less than epsilon for all n greater than or equal to n epsilon. So this is the definition of a sequence to be convergent in R. Okay. So what does this say? Actually, it says that if x is the limit of the sequence xn, then for any arbitrarily small number epsilon, after some finitely many terms, all the terms of the sequence xn is less than epsilon close with the term x. So the difference between xn and x is less than epsilon. So they are very close actually. So just looking at it geometrically, we will get like this. So this is the thing. So if here is x. So for any arbitrarily small epsilon, after few finitely terms of the sequence, we're going to have all the terms inside this. Right? Like there might be finitely many terms here. So after this x and naught, all the terms are inside this. So that's the geometrical view of this. So this is how we define a sequence to be convergent in R. Okay, cool. Let me erase this and then we can see what we mean by limit of a function. So this is the limit of a sequence. Then we have limit of a function. So here function we know R. So we know a function f from R to R. So this is a real function, right? So here we are going to define a limit. So suppose fx is a function from R to R. Now there is something we say as this, limit x tends to a fx. So what is this? This might exist, may not exist. So if it does exist, then it is equal to some real number L. So if there exists some L such that we say this to be L, then we call that the limit of this function at the point A exists, or if not, then it doesn't exist. So when this is equal to L, what is the definition of it? So definition is as follows. For all epsilon greater than 0, there exists delta greater than 0 such that x minus y less than delta. Okay, and here we need to have y not equal to x. Implies fx minus fy. So not fx here, sorry, just a bit of mistake. L minus fy is less than epsilon. Okay. So this is very similar to the definition of limit of a sequence. Okay. So what is this? We are saying is that for any arbitrarily small epsilon greater than 0, we can have some delta greater than 0 such that for all numbers close to x by delta, that is the difference between that number and x is less than delta, and that number is not x. Okay. Then for that number, the functional value of that number is epsilon close to L. Is epsilon close to L. That is the thing. Okay. So also we can define it using the limit of a sequence thing. So this is another equivalent definition. I am not going to prove that these two definitions are equivalent, but yeah, so this is just a review on what we know about R. So I'm just going to mention this. So here we can also say for all xn sequence converging to A. Okay, but here xn can't be equal to A. Okay, so for all xn sequence converging to A but xn not equal to A, we should have f of xn. This is also sequence converging to L. Okay, this is, if this is the case for all sequence xn converging to A, we say that the limit of fx at the point A exists and this is equal to L. And if there is no such L for which this happens, then the limit doesn't exist. This is our definition. Okay. So this is a definition of our limit of a function. Okay. Then we come to continuity of a function. So what is continuity of a function? This is very similar to the definition of limit, but here that L should be the functional value of that point where we're taking the limit. That is the only difference. So what is it? So we say if a function from R to R is continuous. So one thing I'm very sorry for is my handwriting is not very good, but I hope that you all can cope up with that. Okay. Continuous, if R to R is continuous at some A in R. So what does this mean? This means that for all epsilon greater than 0, the definition of this is there exists delta greater than 0 such that x minus y, so a minus x less than delta implies f of a minus f of x less than epsilon. So here this x can be equal to a, right? So here we are also involving the point where we are talking about the continuity. Okay. So again, it's just a matter of fact to check that if a function is continuous at a, then at a the limit exists and the limit is equal to f of a. Okay, you can just verify this. And again, the sequential form of definition will go like this: for all xn converging to a, f of xn converges to f of a. That's it. As simple as that. Okay. So to just view it geometrically a bit, maybe. So if this is a continuous function, then for suppose we are talking about continuity at this point, this is the point where this is a, this is f of a. So for any epsilon neighborhood around it, so okay, I will define neighborhood, but just epsilon thing around it. So any given epsilon, so this is f of a plus epsilon, this is f of a minus epsilon, will get some delta such that, so if we have like this, we can take the minimum of them, so we will have some delta around it such that all this thing is mapped within this thing. That is, for any number here, the functional value of that number is within this f of a plus epsilon and f of a minus epsilon. So this is the geometric interpretation of it. And this is how we define continuity on R. Okay. So one more thing what I was going to discuss, that is a neighborhood. So this is something which we can discuss later also, but let me discuss it here only. So this is a very basic definition. So neighborhood of a point A. So let me say epsilon neighborhood of a point A is the set of all points which is epsilon close to the point A. That is a minus epsilon to a plus epsilon. If this is A, so we take all the points whose distance with A is less than epsilon. So that is the epsilon neighborhood of A. So here you can see, so we write it as this. Okay. This is our notation. So here you can use the notation like this, that if X is in delta neighborhood of A, this implies that f of X is in epsilon neighborhood of f of A. So this is how we can use the notation of neighborhood. Okay. And in the case of definition of limit of a function, there also you can use this, but in that case, so in a neighborhood we have this A, right? So in any neighborhood of A we have this A point in that neighborhood, but we can't consider the point A in case of discussing about the limit at the point A. So there you have to just subtract the A from this set. Okay. So just think about it, it should be clear. Fine. So let me erase this also. So we know what we mean by continuity on R. We know what we mean by limit of a function in R. We also know about a sequence in R. Okay. Then comes a bit more trickier thing, defining differentiability. So yeah. So somehow we will see later that this differentiability and integrability is nothing to do with this here. Okay, so I am just discussing this for the sake of completeness, that all the things we know about R. So we know what we have like differentiability in R. So when we call a function differentiable, okay, so if f is from R to R, we say f is differentiable at A in R with derivative f dash of A if limit x tends to A f of x minus f of A by x minus A exists and is equal to. So if the limit exists, the value it is equal to, we call that to be the derivative of f at the point A. That's it. So this is the definition. Okay. This definition can also be made like having a function gx to be fx minus fa by x minus a and thinking about the continuity of the function gx. That is also a way. Okay. But yeah, it is fine. So this is how we define differentiability of a real function f at some real point A. Fine. So this definition wholly is based on the limit, definition of a limit. Okay. And again, integral also we define in a similar way. So for defining integral in a good manner, we have to define partition and all. So I don't think that definition is given in any like 10+2 discussion. But okay, so I will not define integral to the full rigorous way here, but we know what we mean by integral, right? So it is something like antiderivative and all. So yeah, we know what we mean by integral in R. Somehow we know the intuitive feeling of it. So integration also we know. So somehow we don't need this thing of integration and differentiability here. because the thing we are going to generalize won't take them to. But yeah, so we all know all these things on R. Good. So now just take a quick review that how we define all these things. So I am only concerned about this. I'm only concerned about sequences, functions. So sequences means limit of a sequence, limit of a function, continuity of the function, and that's it. So we are concerned about sequences limit, limit of a function, continuity of a function. So here we just see that for some, like in all the definitions, we have like for some epsilon greater than 0, we have some delta or something, some n epsilon, something which depends on delta, depends on epsilon, for which if the first parameter is enough close to something, then the next thing is close as we want it to be. That's the whole thing, right? So in all of them, we just need something like, here we need xn minus a less than epsilon. For some xn, like after some finitely many xn's, we should have this. And then again, here we need x minus, f of x minus l is less than epsilon. And here you need f of x minus f of a is less than epsilon. And we managed to get that here by having x minus a is less than delta, x not equal to a. Here we managed to get it by x minus a is less than delta. Okay. And here we managed to get it by some after some finite many terms. Okay. So this is in a nutshell what we do to define all these things. But now the question is, okay, so this is what we know. Okay. So now there is a good observation we can make here. That is, given a set of real numbers, given R, we can do all such things. So what is special about R so that we can do all these things? So can we do it in the set of natural numbers? Can we define limit of a function in the set of natural numbers? Can we define continuity of a function in the set of natural numbers? Can we define limit of a natural sequence? If we can, then why only n? For any given general set X, why can't we do this? So what is that thing what we have in R so that we can do this? Okay. So just look at all this. So there is some similarity in this. So what we are doing here, we are just considering x minus y for some xy real number. So we have this wonderful and like amazing thing in R. There is a notion of distance. For some 2 points in R, we have something like the notion of distance. So we know something like what is the distance between x and y. We call them to be the mod of x minus y. Okay, so let's see what we can do here, how we can generalize things. So let us go back to the slide. I just gave a quick review of all the things we know on the set of R. So let's just go back to the slide. Okay. So here we have discussed the analytic properties of R, like limits of sequence and functions, okay. So we haven't discussed limit point of a set. So let me discuss that. Okay. So let me just go back to our blackboard and discuss that. I missed that somehow. So let me define it here only. Limit point of a subset of R. So let A be a subset of R. So we say L is a limit point of A. So L belongs to R. When we say this, if there exists a sequence xn which is in A but which is not equal to L. So any of the terms in xn is not equal to L, and this sequence xn converges to L. Then we say L to be a limit point of the set A. So A should be a subset of R, and we call L to be a limit point of the subset A if there exists a sequence of real numbers in A, but none of them is equal to L, and that sequence is converging to L. In that case, what we say is, we say that this Xn, we say that L is a limit point of the subset of our A. So again, here what we need is the concept of a limit of a sequence. Okay, so if in some abstract set X, we know what we mean by limit of a sequence, then somehow we can manifest something like limit of a function. We can manifest something like continuity of a function. We can also have something like limit point of a set. So we can have many things actually. Okay. Also, while defining neighborhood of a point, epsilon neighborhood. So let me write it like this only, epsilon neighborhood of a point. What we need is x minus epsilon, x plus epsilon. So here also we need that this is how can we write this set? This set y in R such that x minus y is less than epsilon. So this is the set theoretic writing of this set, right? This interval. So we are taking all the points in R which is epsilon close to x. So here also we need this thing, mod of x minus y. Okay, so this is the observation here. So many things we are doing on the analysis of R, we are just using the property of distance of 2 points on R. Okay, so now let's see how we can generalize this. Okay, so fine. Then we come to the generalization. So first of all, why we need to generalize? That's the first question to ask. So that is a very good question to ask. And from the mathematical perspective, the thing we do always, like we try to do always, is we want to do some structure. We want to have some structure. We want to discuss the properties of a structure. So when we have a structure, then we try to unfold the properties of it. So that is what we did in the case of R. Now we have to think, like this is a mathematical way to think, that in which all other cases we can do some similar analysis. So why only R? We can do it in a general set X. We can have all such properties like sequence, limit, continuity, and all such things. So we don't want to restrict ourselves to R. We want to do all such things, properties we did in R, for any general set or for a bigger set. That is what we want to do. Okay, that is a philosophical way of thinking. So in any case, there are many other examples also. What we can do here, we want to do it in a larger set, a general set, a general manner. So that is a philosophical reason to try out some generalization. Then we have our beautiful observation. That is, all we need is mod x minus y as a believable notion of distance between two real numbers x and y. So to have all these things like limit of a function, limit of a sequence, limit of a continuity, and then we have limit of a set, and then we have definition of a neighborhood. So all these things, we only need this x minus y, mod x minus y as a believable notion of distance between two real numbers x and y. So then the obvious, what we want to think is, if for any given set X, if we have a believable notion of distance, we can do all such things. Okay, so let us see. So we need to have a set with a believable notion of distance. That's all we need to have. So if we have a distance on a set, we can do all such things like defining neighborhood, defining limit, defining sequence, and all such things, defining continuity. So maybe you are not totally convinced that why we can do there. So we'll get to see the examples and reasons why we can do that there also. But yeah. Then we are now going to define the metric space. Okay. So let's just define metric space. So now we are going to define the definition of the general metric space. Okay. So let's just clear the canvas. Fine. So yeah. To define a metric space, let me just first define something called a metric. Let X be a set, non-empty. Okay. So for any given set non-empty, let D be a function from x cross x to x. Sorry, x cross x to R. we call D to be a metric on X if, so here goes the definition, it satisfies if, so there are few properties to be satisfied, D of X comma Y should be greater than or equal to 0 for all xy in X. So D is a function which is taking values from X cross S, X Cartesian product with X. So what is that? So just I want to make this clear. So this is the set of all ordered pair xy where X and Y both are in X. So D is a function taking input from here and giving output in the set of R, set of real numbers. So it is called a metric. It is called a metric on X if D of xy is greater than or equal to 0 for all xy in X. Then D of X and X is equal to 0 for all X in X. And the third is D of X comma Y should be equal to D of Y comma X. That is also for all xy in X. And the fourth is, so maybe I will write the fourth here. Okay, so let me write it here. And the fourth is D of X comma Y plus D of Y comma Z will be greater than or equal to D of X comma Z for all xyz in X. Okay, so this, if there is some function D from X cross X to R satisfying all the four conditions, then we call D to be a metric on X. Okay, so the first condition we call it as non-negativity. And this is equality, or you can just take it as the both of them, you can just consider that there is non-negativity and equality holds only if X is equal to X, like X is equal to Y, like XY both are the same. Okay, then this is called symmetric property. And the fourth one, the most important one, this is called triangle inequality. So I am quite sure you all can relate the fourth condition with the triangle inequality we know in R. Okay, so this is how we define a general metric on a general set X. So for any given set X, for any given set non-empty set X, if we have a function D such that all the four conditions are satisfied, then we can call D to be a metric on X. Okay, so here comes the thing. So our motivation was to generalize the things we did in R, did in the set of reals. And then we observed that all we need is a proper function of distance, a proper notion of distance. We had in R the thing mod of X minus Y. So that was the distance between two real points, right? Distance between X and Y, where X and Y both are real numbers. So now we are trying to have a proper notion of distance for any general set X. Okay, so this was the intuition behind the definition. And we can see all the properties are the properties we want to be satisfied for a distance. So if we consider distance between 2 points, they always should be non-negative. And so if we consider the distance between that point to that point only, that should be 0. And then again, the distance should be symmetric. Distance between xy should be equal to the distance between y and x. So they should be symmetric. And then they should satisfy the triangle inequality. So we are just doing that. We are just taking the intuitive thing we have for distance in our head, and we are just writing them down as the conditions to call a function D to be a metric function on X. So this can also be called distance function. You can also call it distance function on X. So for any given general set, non-empty set X, we can have a distance function on X, like if all the conditions are satisfied. Good. So let me just give you a few examples to make it comfortable. Examples. Okay. So let our first example be our basic motivation for all this. That is when x is equal to r and the d of x comma y is equal to mod of x minus 1. So this is the thing we had in R, right? So we had a set of real numbers, and there we had the notion of distance to be mod of x minus y between two real number points x and y. So we can just easily verify that it satisfies all the points. So it is greater than or equal to 0 for all x, y, and then again it is equal to 0 if x is equal to y. And then the famous thing, the triangle inequality we know about R is this. So which says that d of x comma y, as we define d of x comma y plus d of y comma z is greater than or equal to d of x comma z. And then again it is symmetric. So this is a proper, like this is a valid metric defined on R, right? So this is a valid metric defined on R, this d. Okay. Again, just let me just make it example number 2. Take x equal to R, take d of x comma y to be some constant multiple of this. So let it be 5. So if we define the d as this way, so d is a function from R cross R to R. So here d should be a function from R cross R to R. Like in general x cross x to x, and here x is equal to R, so R cross R to R. And here also d is a function from R cross R to R. So just check that here also all the properties are conditions are satisfied. That it is non-negative, it is symmetric, it is 0 when x is equal to y, and it also satisfies triangle inequality. So in this triangle inequality thing, it is just 5 times here. In the second example, it should be just 5 times in both sides. So this d also satisfies all the given conditions for d to be a metric on R. So this is also a valid metric on R, right? So that is the thing. So we are defining distance. We are defining a notion of distance on a given set x. So here for the given set to be R, we have distance, like we can define distance as in our usual way. And okay, so just to mention this distance, we call it to be the d usual. Okay, so we write it as du, that is usual metric. So this is the usual metric defined on R. Because we work with this metric in many places, so we call it to be the usual metric. Okay. And here also, this metric is quite similar to the usual metric we work with, but it's just a constant multiple of this. So when we are working in this setup, like dxy equal to 5 times mod of x minus y, then if someone asks you that what is the distance between 1 and 3, so that should be 10, right? So this is not 2. This is no more, the answer is 2. Okay, when you're working on distance function to be 5 times mod of x minus y, the answer is 10. If you want to find out the distance between 5 and 10, it should be 25. So likewise. Okay. So this is how we can define various metrics on R. You can just take any constant multiple, like 5 is nothing special here. You can take 10, 15 or anything. Okay. So it's fine. Now let us go to our next example. Example number 3. So here let x be R square. We want to define a metric on R square. How to define a metric on R square? So what is the intuitive thing? So if there are 2 points in R square, we call this to be the distance. And what is this? If it is x1, x2, y1, y2, then we say this to be what? y1 minus x1 whole square plus y2 minus x2 whole square. This is a geometric thing, root over of this. So this is the length of this. We call this to be the length of this. So we can define metric intuitively over R square. So d of xy should be, and what is xy? So x can be just x1 comma x2. So x is a point in R square, right? So d should be a function from R square cross R square. So what should d be here? A function from R square cross R square to R. right? So let the x be some x1 comma x2 and y be some y1 comma y2. Then we define d of xy to be root over y1 minus x1 whole square plus y2 minus x2 whole square. So it is a matter of fact to check that it satisfies all the four conditions. So it is obviously non-negative. Again, it is obviously equal to 0 when x is equal to y. If x is equal to y, then x1 is equal to y1, x2 is equal to y2, right? In that case, it should be 0. Again, it is obvious to check that it is symmetric, but now to check it is triangle, it satisfies the triangle inequality. It might require a bit of work, but that is your exercise. So exercise, check triangle inequality. Okay. But it should be intuitively clear that it is a valid form of distance, because geometrically it is like a triangle, and so it will obviously satisfy the triangle inequality. The sum of these two will be greater than or equal to this. So yeah, so this way we can define a metric on R square. So when we have a metric on R square, we can do all such things like limit point, limit of a sequence, limit of a function, continuity in R square, right? Okay. So we will go to that later, that how we can define all these things on a general metric space, a general set with a metric. Okay, so this is a valid metric on R square. Fine. So let's go to our next example. Example number 3. Sorry, example number 4. Okay, so here let x to be r power n. Okay, so this is r cross r cross r till n times. Okay. So here we define d of x comma y to be. Okay, so what will be x here? X will be something like n tuple, and y will be also n tuple. So let x be this and y be this. Then we define x d of x comma y to be very similar definition, y1 minus x1 whole square something yn minus xn whole square. So this is a very obvious extension of R square, right? The metric we define on R square. And again, it is a matter of fact to check that it satisfies all the four conditions. The first three will be evident, and you have to do some work for the last one. That will also be easy. Okay. So for this, so let me give a hint to define for general R power n to show the triangle inequality. You need to use Minkowski inequality. Okay, I think you guys should be comfortable with this, or just try Cauchy squares or something. You can do it. You can do it. So just try again exercise. Prove triangle inequality. Okay. Try to show that it satisfies a fourth condition for D to be a valid metric. Okay. So that's it. So now we know that we can define a metric on R square or in general R n. Okay. And again, like all these metrics are called Euclidean metric. So there is a name for all this metric. Euclidean metric, or this is also denoted as du, or the usual metric. So this is the usual metric on R power n. Okay, in R power n, this is the usual metric. This is the metric we work in the case of geometry or Korean geometry or anything like that. Okay, good. So let me give you another example. So there might be an obvious question to ask that these are the metric we can think intuitively, but are there any other metric we can define on R? Okay, so in R we can define many metrics, like right. So we can define mod of x minus y to be a metric, that is our usual metric, and then we can take constant multiple of it, any constant multiple of it, that will do. But they are quite similar, right? So we may have to think of a different, like a quite different metric on R or R square. So okay, so our next question should be that Yeah. So another very good question to ask is that can we have a metric on any set X? So we have a metric on, okay, so let me just write it down. So we have a metric on X R. So if X is R, we have a metric. In general, if X is R power n, we have a metric. That is our very intuitive metric. What we think intuitively, we are just writing down rigorously. So we have a metric on R power n for any n natural number. Now for any given set X, can we have a metric? That is, can we have a D from X cross X to R such that it satisfies all the four properties, conditions? Okay, so the answer is yes. The answer is yes. So the question I gave, the answer is yes. So for any non-empty set X, we can have a metric defined on it. Again, you can just stop the video for a few minutes and think that how we can define a metric on X in general, for any general X. Okay. So in our next example, we are going to see that how for any general X, general set X, we can define a metric on it. Okay. So let's say it is example number 5. Okay. So here, let X be a non-empty set. We define D of X comma Y. Okay, so D is a function from X plus X to R. We define D of X comma Y to be 0 if X is equal to Y, 1 if X is not equal to Y. Okay. So firstly, this function is non-negative because either the value is 0 or the value is 1. So it is non-negative. And again, it is 0 if and only if X is equal to Y. D of X comma Y is 0 if and only if X is equal to Y. Again, it is symmetric. By definition, it is symmetric. And then for triangle inequality, you can just check. It is very easy to check that the triangle inequality is also satisfied. Okay. So D is a, so you have to check this, but the checking process is very easy. D is a valid metric on X, right? So for any general set X, non-empty, you can define a metric on it. So that is not a very big deal. Okay. So just take a corollary kind of thing. You can define this, and okay, so we call this metric to be discrete metric. So this metric by definition is called discrete metric. So you can define discrete metric on R. Okay, define, for example, just you can define discrete metric on R. That will be like the similar definition. In that case, what is the distance in 1 and 2? It is 1. What is the distance between 2 and 5? It is also 1, right? So it is a weird metric. Okay, you can't think of it intuitively, but it is a metric. It is a proper metric you can just think of on any set. Okay. So this is a metric we can define on R, we can define on R power n everywhere, and which is not very similar with the usual metric we defined on the set. Okay. Then again, we can define let me just end with this example. So it will be rather an exercise to check that why this is a metric and is it intuitive or it is not intuitive or like that. Okay. Let me make this a different example number 6 maybe. So this is called a maxima metric. So we define dm from R cross R to R. Okay. So this may be a metric on R. Okay, here X is equal to R. So this is something you have to check. dm of xy is equal to maximum of mod of x and y mod of y if x is not equal to y, and 0 if x is equal to 0. Okay. So this is how we define the maximum metric on R. So okay, so it is something to check that it is a metric or not. So this is exercise. Check that DM is a valid metric or not. Okay, so it is exercise, just check it, and by now you should be clear that how we are approaching towards this. Okay, so we need to have a metric on sets, on a general set. If we have that, we will see that what all we can do there. Okay, the first purpose is to, if you are given a set and a metric defined on the set, you have to check that that is a valid metric defined on the set. Okay, so there is a very intuitive notion of this, right? So when you are having a metric on a set, it is quite similar to a set like R, where you have the notion of distance between 2 points. When you have this function D, there is complete sense of talking about distance between 2 points. So that is what we needed, and that is what we have now. Okay, so okay, so let us just end with defining what is a metric space. So now we know that what is the meaning of a metric defined on a set, and the matrix definition of metric space is very similar from this. So given a set X, again non-empty, and D, and what is D? D is a function from X cross X to R, a metric, so it should be a metric on X. Then this thing, the set together with the metric, we call this to be metric space. So for example, the metric space we worked with so long is R comma du. That is the usual metric defined on R. What is du? Mod of x minus y. Du of x comma y is mod of x minus y. This is a metric space. So we did all such things like continuity, limit, everything in the special metric space R comma du. Okay, so that was it, and then in our next lecture we are going to see what all stuff we can do in our general setup that is in a given metric space X comma T.